This is PH1501 Unit 1 Vector Analysis by Dr. M.R. Gadhvi. This is again I would like to remind you, this is our textbooks, that is Introduction to the Electrodynamics by David J. Griffith, publication Pearson. I know that few students are joining the college later, so it's kind of reminding again you. The motive is to remind you again the book. Okay, let's rewind the last lecture in very brief 1 or 2 slides. We have observed that this is basically your 11th and 12th grade discussion, so in a way you are knowing very well, but anyway, as a part of syllabus we should go through again. The vector A is defined as a magnitude by putting into the mode. In some books you may find it out without mode and only character A. That is also a way to represent the magnitude. Addition of a two vector, parallelogram law of addition is very well known, or wherever you are going, let us say B vector is like this, and then at the head of the B you are adding the tail of a, and then this is the A of B, or other way, if this is the A, because this is parallelogram, then on the head of the A you are putting the vector B because it is parallel to that, and that is again the A plus B. The same way, multiplication of the vector by a scalar, that means M is a scalar and you are multiplying with the A, so M times A becomes a little bit larger than this. It depends on the value of the M. The subtraction is exactly similar phenomenon like the addition, because it is basically A vector A plus minus of vector B. So basically it is like a B is here and A is here, then this has become the from head of B to head of A, that becomes the A minus B, or you will go with the head of A to head of B, so it becomes the B minus A. With the parallelogram you can understand the phenomena very clearly. Vector algebra in part 2, where you can say the scalar product, the dot product, it is also known as, so it's shown by a dot, so it's a vector A dot vector B. It shows like the product of their magnitude times cos theta, or the cos angle between A and B. Magnitude of a vector is given by a magnitude in a mod sign, and that would be given by under root of the square of A. So this dot product with the itself the same unit, that is given as A magnitude of vector A product with the magnitude of vector A, cosines between the same vectors, and same vectors, that means it is parallel to each other, so the angle between them is 0, cos 0, that is 1, so it's basically A square. So magnitude of a vector is also given by the A square and root of that, so that would be the A. So that way also you are proving it. Unit vector is shown by the A cap, its value is a magnitude is always 1. Zero vector, the magnitude should be 0. So when you multiply with the zero vector to any vector, the outcome becomes 0. The vector product of two vectors, or it is a vector product, the earlier one was the scalar product, now we are talking about the vector product, so that is A cross B, and that will be the product of their magnitude times sine theta, and the theta, that is the angle between that two vectors, and the direction and the dimension of the outcome or the product or the vector product, that would be always perpendicular to the plane framed by that two vectors. So here the vector production is of A cross B, that means A is you are going to take across with the B, so this angle and if you use the right hand side thumb rule, then thumbs will be coming out of the page, and that's why it's showing up. Okay. You can also show any particular vector in their two components. Let us say this is unit vector n1 cap, this is unit vector n2 cap, then combination of the AC n1. So the AC segment, that is basically the segment that is not the scalar, so I mean not the vector, it's the scalar one. So a certain multiplicand number to the n1 cap plus certain scalar value or numerical value multiplying to the n2 cap, and that is nothing but your A. So AC vector plus BC vector gives the vector A. So basically you can represent any vector in combination of a two perpendicular vectors. Same way in the case of a notation of the vector product and the dot product, also you can represent any particular vector. Okay, let us take an example on the basis of the scalar product what we have learned. Not at all difficult, but yes, you will get it a little bit more flavor about how exactly we can work out. What is it is written in example 2, find the angle between the face diagonals of cube. It was written like that, but I modified the sentence like face diagonals of a cubic unit cell. I think with the help of the solid state physics, you are knowing very well what it means by unit cell. It's a fundamental block of any crystalline structure. In nutshell, unit cell, that means their size will be of a unit, and therefore if this is a cubical unit cell, then the y coordinate will be maximum 1, the x coordinate will be also 1, and z coordinate will be also 1. So the cutting edge of the x axis, cutting edge of the y axis, cutting edge of the z axis, that would be 1, and that's why it's called the unit cell. Okay, now how to calculate this? So let's begin with the origin. So I have considering the origin over here. So now I have asked to find it out the angle between the face diagonal. So this is a one face, that is a YZ plane, and where I am drawing one diagonal in that particular plane, and that is defined as a B. The another plane I am choosing, that is XZ plane, and that is this one where I have drawn the diagonal, and that is E. Okay, how exactly it looks like? So I have just drawn a pictorial diagram, so it will be easy for it. One is a sky blue plane, that is your ZY plane, and one is a yellowish plane, and that would be your XZ plane. And you need to, and there these two diagonals are there, and you need to find it out the theta between them. So that is our motive. Okay, now what will be the position coordinate over here? So this is in the XZ plane, so only X coordinate and the Z coordinate will be available over here, and Y coordinate is absent. And if I do have the two coordinate, this is the origin, this is the destination, or this is a tail point, this is the head point, then on this basis I can make the vector A, and vector A can be given by vector A is the head point minus tail point in the direction of x cap, 0 minus 0 in the y cap direction, and 1 minus 0 in the z cap direction. And therefore the vector A, I can write it like this: 1 x cap plus 0 y cap plus 1 z cap. So even though you are not writing out the middle factor, that is fine. So 1 x cap plus 1 z cap, or sometime it is written with the book x cap plus z cap, because one multiplicand factor is we are not writing, it's valid. Suppose I will choose the point B. B is in the YZ plane, so it's a 0 1 1, and therefore the B vector will be arises like this. Now what should I do? So I have a vector A, I have a vector B, and this is my same figure. So how to find it out? The angle between this face diagonal, and that's why what I will do first, I will do A dot B. A dot B, that means only x component having a dot product with the x component, y component having with the y, and z having a z. The mutual component multiplication, that is whenever they are orthogonal like a x to y and x to z, that always comes out to be 0 because their angle are pi by 2. So with elimination of those remaining the mutual orthogonal component, only parallel planes will be considered. So x cap with x cap, y cap with y cap, and z cap with the z cap. So outcome is 1. So my LHS is 1. Okay, and so LHS is 1. This is 1. And now AB cos theta on RHS. So A value, how we are going to find it out? The value of A, under root of square of their each component. So 1 square plus 0 square plus 1 square, so it will be under root of 2. Similarly, the B will be also under root of 2 cos theta. So root 2, that is 2 cos theta. If these two, I will take it on the left hand side, so it becomes the 1/2 is equal to cos theta, and 1/2 cos theta is equal to 1/2. That means theta is equal to cos inverse of 1/2, or you can say it's a theta is equal to 60. That means theta is this one. Now I would like to suggest you to just check it up at your level, that measure the theta between the YZ and the XY face diagonal. So YZ, that means this is Z, and this is the a vector B, and XY, that is the bottom one. So you have to take a x over here, the vector A over here. Are you getting me? If this is a xy, so you have to find it out this coordinate. So it would become xy. So it's a 1 1 0. Z component is missing, and that way you can having the vector A and vector B will be as it is, and you will get the idea what is the theta is available. Similarly, you should check it out with the another example what I am suggesting you, that is ZX versus XY face diagonal. Okay, let's go ahead with the few more property of this one, and that is a vector algebra by the components. So basically till the point we have just seen it's a addition by their numerical values, but now actual thing is by their components. So this is a position vector. Let us say this is a vector any stray vector, then take their projections on each axis. Then this is the y axis, this is x axis, that is z axis. So the corresponding projection, that is the z component, so it's a AZ. So this would be your projection on the y axis. So that length is equivalent to the AY, and multiply by with the y cap. So the direction is also represented here. This dotted line is representing the AX into x cap, so that is equivalent of the x direction. As we are aware, the x direction and similarly the z direction. So A plus B is basically a combination of a AX x cap plus AY y cap plus AZ z cap. The main underlying part is you have to add the component in the same direction, that is x cap or y cap or z cap. So AZ plus BZ, AY plus BY, and AX plus BX only. Secondly, the rule to multiply that one, so A into vector A. Remember that in the Griffith book the vectors are not shown by the arrow, but they are just showing by the bold faces. That is also considered to be a vector. So when numerical any scalar multiplying factor is there, then it would be a multiplying to their component, not to the unit vector. So ax x cap, ay y cap, and az z cap. That way you have to visualize it. Similarly, to calculate a dot product between them, so a dot p, so as just we have seen in the example, so ax x cap plus ay y cap plus az z cap dot with a bx x cap plus by y cap plus bz z cap, where I will be looking only with the x cap, y cap and z cap is equal to 1, because their cos angles are 0, 0 is equal to 1, and the orthogonal component comes out to be a 0. So the final yield product will be ax plus ax dot bx, so the product of their component of x direction, product of the y component plus product of the z component. So it will be a certain numerical value because it is a scalar product. This is said to be a scalar product. Okay. Now the same terminology, but this is a part of a book. That was my slide, and this is a part of the book. So this is how we can check it up over here. The same story, ax and axy, the summation of there, the multiplication of the rule, and so on. Okay. So sometime they are asked to calculate a dot product of the same component. Then what it is? So a dot a. So it would be just a simply squaring of the a square plus y square plus z square. So basically a is under root of a square plus y square plus z square. So it's written very importantly here, to calculate the dot product, multiply like components and add in a particular way. So this is how the addition is taken place, but this is a squaring of the vector. So where you have to just add their respective component and find it out their magnitude. Okay. So this is, if you like, the three-dimensional generalize of a Pythagorean theorem. Then you can having the x cap cross x cap is equal to y cross cap y cap is equal to z cross z cap, and that is always 0 because sine theta, because when you dissociate this one, it becomes the product of their magnitudes times sine and angle between these two vectors. So it becomes the x cap multiply by magnitude of x sine theta, theta is angle between them, and these both are in x direction, so angle is 0. So sine 0 is equal to 0, and therefore the outcome will be 0. But when they are both are orthogonal, so that is the x cap y cap or y cap z cap or z cap x cap, so that's how it become in a z direction, the third dimension. That you can prove it by the right hand side thumb rule. Okay, and that's why this is z, but this is a non-distributive, and therefore x cross y cross is equal to, you cannot write y cross x cross x y cap cross x cap cross, but you have to put the negative sign because one will come out from this page, the second will go inside the page. In case of a cross product, you can put it in the terms of determinant also, where the first row will be the direction of the unit vector, so it's a x cap y cap z cap. The first candidate, that would be the second row. The second candidate, that would be the third row of your determinant. In nutshell, what we have seen the point till the discussion, the x vector added to the y vector, you can rewrite as a y vector is added to the x vector because they are commutative. The law of addition is a commutative. X vector plus y vector as a bracket is added to the z vector, that means the summation of x plus y is added to the z vector, then you can rewrite the same thing like a x vector is added to the summation of y plus z, because the law of addition is also associative. The vector x is added to the null vector, it's remain unchanged, so unaltered. So that is the importance of a zero vector. In case of a multiplication, there are few things to be remembered. The alpha into bracket beta x vector, you can rewrite the thing alpha into beta times x vector, and that is law of associative for the multiplication. Alpha plus beta multiply to x vector, you can write it out as a part of distribution. So alpha x time alpha vector x and beta times vector x, or alpha times x vector added to beta time x vector, and that is how the distributive law of a multiplication. And the lastly, alpha of x vector added to the y vector, you can rewrite as a alpha x vector added to the beta times y vector, and that is said to be a law of multiplication for commutative, or the law of multiplication is also commutative. Okay. Let's go with the third stage, that is a triple product. Again there is a two part, scalar triple product and the vector triple product. Let's start with the scalar triple product. It could be written like A dot B cross C. Generally in case of a mode A dot B cross C, because it's a scalar one, and that is nothing but the volume of a parallelogram. You can have a vector B and vector C. When you have a vector B cross C, that means you are taking vector B cross C. If you use your right hand side thumb rule, then the vector or the product of this B cross C is coming out of this page, so it will be in the direction of the n cap, and basically B cross C will define this area of a parallelogram, and that many times height times of that area times of the height of it in the direction of n cap, and that's how this dot product or the scalar triple product is nothing but the volume of a parallelogram. Okay, so A dot B cross C, and since it is also scalar one, so it's associative, and so you can say that B dot of C cross A or C dot of A cross B, it is the same one. So such kind of questions could be asked, that I can give you the vector A and with their component, vector B with their component, and vector C with that component, and if I will ask you that prove that A dot B cross C is equal to B dot C cross A, then both LHS and RHS you have to deduce accordingly. Okay. In continuation with this, you can also put it in terms of the determinant. This might be also you are knowing, it's A dot B cross C. So the very first candidate, that should be with their component at the top or as the first row, the second candidate as the second row, the third candidate as the third row, and this determinant outcome is nothing but the volume of a parallelogram. Okay, and not that dot and cross can be interchanged. That means look at here, A dot B cross C is equal to A cross B dot C. That means they are commutative distributive as well. You can utilize this property to find it out the volume of a parallelogram, as well as you can having a dimensions like a pyramid, then you can find it out the volume of the pyramid with the same logic. So vector triple product, the earlier one was the scalar product, now it's a vector product. So it's a A cross B cross C, and it is very well known rule known as a BAC-CAB rule or BAC-CAB rule. That means the central candidate should be written first with the rest 1 2, that is BAC minus central candidate the next candidate of the central one, that is become ahead as a CAB. So BAC minus CAB. Here also it could be asked that I can provide you the vector A, vector B and vector C, and I can ask you to prove the LHS is equal to RHS. The same way it is not easily can be written like A cross B cross C. You cannot write directly C cross A cross B because the direction will be changed, so it's a negative. When you change the cross product, like the product of A cross B is taking a cross product with C. If you interchange the location, that C comes first and A cross B comes later. If you look at here, the bracket is first and C is later. If you change their position, the direction will be changed according to the right hand side rule, right hand side thumb rule. And still this is also true for the BAC-CAB rule, and that would be with the preceding with the negative sign. Okay, and actually the first term is always positive, but since you have a negative sign, so first term is negative and the second term is become negative, negative plus, so it become the plus 1. So keep in this mind. There is also possibility is a 4 vectors are given A cross B dot C cross D, as it is a distributive. So the A dot C, then A dot with D, sorry, A dot C, then B dot D, so that is your first vector, minus then your A and B with the product of C and D get over. So now you will be taking a product of A dot D and then B dot C. So if you look at here how we are exactly doing, this first candidate is multiplying with the first candidate, so it's a dot C. Then you have the second candidate of your first bracket with the second candidate, because you have already done with the first candidate. So A dot C and B dot D, and similarly later on the first candidate with the second candidate of the next step, so A dot D, and another one will be the B dot C. So same way you can put it in the A cross square bracket of B cross C cross D, and you can put it in this way. Here you can write it out, the combinations of their distributions, and the value of A, value of B, value of C, value of D in the component part, if they are providing you, you should be able to produce the LHS and the RHS product term. Okay, where exactly we are looking the few examples of a cross products. So suppose you have learned about the interaction of a charged particle Q with the magnetic field. So this is a magnetic field, this is a charged particle is rotating with the velocity of the v. Then the v cross b, if you taking the right hand side thumb rule and taking a cross product of a v was cross to b, then at the point of the radius, the torque will be applied or the force will be applied in the direction of the thumb direction, and that would be your upward direction or the direction coming outside the page. So v cross b, that is coming outside, so force in that particular direction. The another application is known over here on the circular disc. When you apply the force on that particular point, then the force will be in this direction. So that force I can put it into two component, f cos theta and f sin theta. F cos theta is parallel with the r, so it doesn't make us change in that particular direction of the wheel, but yes, f sin theta will making a active role in this force, and therefore you can having the torque in the direction of this particular axle or across what the radial component r is pivoting. So the axle, the torque will be parallel to the exerted to parallel to the axle. Okay, so the last point, the position and displacement and the separation vector. What it mean by the position vector? So any vector with reference to the origin, the any target what you are destinating by a particular vector r. So let us say here the red vector is referred by the position vector. In general, we dealt with the Cartesian coordinates, so that is a or three orthogonal axes are acceptable, and that is the x direction multiplied with the x cap, y direction with the y cap, and the z direction with the z. So this is a parallel with the z axis. So this particular dotted line, that many longer component on the z axis. So how to find it out? A unit vector, so the vector divided by its magnitude, so x cap plus y cap plus z cap divided by the square root of the square of their component magnitude, so that is the x square plus y square plus z square. This you can look at the infinitesimal small displacement in the direction of the r itself, so that is referred as infinitesimal displacement vector, that is a dl. Remember that in the direction of a vector r you are changing a little bit variation in the displacement, and that is called the dl. So the dx x cap plus dy y cap plus dz z cap, since it is in the same direction, so it is a dx x cap plus dy y cap and dy z cap. Suppose you having a one test charge over here, and the test to be measured that charge or particle over here. So on this particle, which is shown by the position vector r, where you are looking what is the effect of the charge particle over here on the x prime y prime z prime over, and how the field of the x prime y prime z prime coordinate charge is exert a field effect on the particle located at the x, y and z. So you having a two position vector, if you take the difference of this two position vector, you can having the separation vector. So separation vector, you can look at here, separation vector is a small curly r, bold one. So if we will be writing in a notebook, it is a small r with the arrowhead sign, and take a difference of that two vectors, so vector r minus vector r prime. So the head position vector minus tail position vector, so r minus r prime. So the coordinate of the head is x, y, z, and the tail coordinates are x prime, y prime, z prime. So you are taking a difference of that their coordinates with the direction of the x cap, y cap, z cap. So if you want to take the magnitude of such kind of a displacement vector, then without bold, or you can put it in the mode. So mode of r minus r dash, that will be the squaring of their summation of the square of their component, rather the square root of the square of square summations of their component, and therefore under root of x minus x dash square plus y minus y dash square plus z minus z square. So the way you are finding out the displacement, that is this vector. So their component or the summation of the square of their component, so x minus square उसका square, y minus y dash का square plus z minus z dash का square, और उसका अंडर रूट ले लिया. So you are finding out the component, the magnitude of this one. And if you are taking the vector displacement vector r divided by its magnitude, so that would be the unit vector of. So by chance I will provide you any particular displacement vector, then I can ask you as a 3 quantity to determine. So if I will provide you a 2 coordinate x, y, z and x prime, y prime, z prime, if I provide the 2 coordinates, then I think one can able to produce this vector r dash. And once you having a displacement vector r, you are able to produce its magnitude, and once you are able to produce this magnitude, you are able to deduce the unit vector of a displacement. Thank you so much for paying attention. Stay home, stay safe. Thank you.